Hey folks, this is Major Jones here to talk to you about out-of-order execution, which is the last structural change to our pipeline we're going to talk about, which to potentially improve our performance. So our goals today are to describe what that architecture looks like for doing out-of-order execution, and what are the consequences of that. So we got two new data hazards we have to worry about, and we'll talk about at least one technique called register renaming to address those two new data hazards. So let's get started. Okay, for a processor that executes instructions out of order, the basic philosophy is if I've gotten multiple pipes from my multiple issue processor that I can execute instructions, then why not just grab, fetch a whole bunch of instructions all at once, and then try to send them in any order possible to keep this pipeline, all these pipelines full, in order to not have to wait for my instructions, so I can get more efficient operation. I can do more in less time. I can get higher performance. So a counterpoint, right, was to go back to our standard multiple issue processor. Well, if there was a restriction in this case in terms of what instruction each of these pipes can perform, then I had this potentially a scenario where I'm less efficient, right? This first issue packet here to this multiple issue processor has a no-op in it, because the first two instructions were both arithmetic instructions, and I just have one arithmetic pipe, at least in this example here. In a multiple issue, an out-of-order execution processor, the actual processor can sort of send the add instruction to the ALU pipe, and then as long as there are no data hazards, sort of just kind of scan downward to find the next instruction to fill this memory slot. So I might have just sort of skipped down here to this load instruction and sent the load instruction to this pipe here that handles memory. And with multiple pipes, that just kind of happens at a slightly larger scale. And the hope is that, again, I can get much better performance. There are three purple boxes you see here that sort of enable my processor to execute instructions out of order. The first is called register renaming, which, as I mentioned just a minute ago, is the solution to some data hazards. So we'll get to that in just a sec. The last two here are called my load store unit and my commit unit, which are kind of names for very similar things. In a processor that's executing instructions out of order, although that can happen, although instructions can execute in any order they want, in many cases the programmer sort of expects memory values or register values to be written in the order that they sort of show up in the code. So most processors will, even if they're out of order, they will try to commit in order. They'll have an in-order commit or an in-order load store unit. And so these two purple boxes here basically will receive values from the instructions that are executing to say, hey, write this value to this register or write this value to memory. And what they'll do is kind of hold on to certain of those instructions if they completed early, until they're able to sort of store to the register file or store to memory in the order that the instructions first appeared in the program. And that just ends up making most people's lives much simpler. There are out-of-order commit processors, but they get much more complicated. So this is just kind of to help put the instructions are executing out of order. We at least put the memory accesses kind of back in order. Now, to talk about register renaming, we have to identify the fact that if we're going to execute instructions in any order we want on the processor, I have two new data hazards I have to worry about, which are called write after read and write after write data hazards. And so they kind of come about in this way. You can see here I got a little sample code where I'm trying to add R1 and R2 into R0. And then right after that, I'm loading a value into R1. And definitely I run into a problem if these instructions are executed out of order, if they're switched around, because the value in R1 is presumably set somewhere above this code, and it has a value that I don't want changed. At this point, when I'm loading it with a new value, I'm presumably done with that, right? I'm done with R1. But if these instructions execute out of order, then I sort of stomp on whatever value was in R1 that should have been used by this add instruction, and the add here gets the wrong value because R1 has whatever was loaded into it in memory. So that's a no-go, right? I got to figure out how to deal with this write after read hazard. I also have something called a write after write hazard, and this example here kind of depicts that, where I've got something very similar. I'm loading into I'm adding R1 and R2 into R0. Right after that, I'm loading something into R0. So again, the presumption is that I'm sort of done with R0, although for whatever reason it was very important to the code that R0 be written here with this add instruction. But it's here that I give R0 a new value, and then I have an add instruction which is using that new value to perform some addition. Okay, well I have another problem if these instructions come out of order. Okay, so my arrow is not pointing to quite the right thing, but you can see here, if my add and my load instruction up top gets flipped around, then the value that this add instruction sees down here, which should have been the one loaded into it by this load instruction, is instead the result of this addition of R1 and R2. So again, by trying to write to a register after I've already written to it, when some register down the line is trying to use that value, I get erroneous results if these instructions are flipped around. So that's what's called a write after write hazard. The solution to this is called register renaming, in which the processor assigns every destination register its own unique value, and then later on sort of works out how they map to real registers. And so maybe I should clarify that. These two data hazards are called false dependencies, and I kind of alluded to it so far by saying, when we have these instructions, this ordering of instructions, we are sort of presumably done with whatever value was previously in R1 because we're loading it with a new value. We're intentionally squashing it. So that's what's known as a false dependency, because in terms of the actual program I'm trying to construct, the meaning of R1 changes between these two lines, right? Previously, R1 has a value which is significant to this add instruction, and now I'm giving it a new value, so it has a new, significance to my program. The only reason why I'm using R1 in both cases is because my processor has a limited number of registers, and and I have to some extent sort of reuse registers for different purposes. And so this is what's called a false dependency, because it's not necessarily that like this instruction here needs the value in R1. It's just that they happen to be referring to the same spot. I have the same problem over here. This is in contrast to the data hazards we saw several lessons ago, which are called true dependencies, because I'm writing to a register and using that same value, for the same meaning. And I have this data hazard that just occurs because of the way the pipeline's set up. One is not written to until after I need it for a subsequent instruction, and so I have to work out that true dependency. This, like I mentioned, is what's known as a false dependency, because even in this case, I'm when I rewrite to this register, I'm giving it a new a new significance, a new importance, a new value in my program. And so the way register renaming works is to think of this almost like I actually kind of think of it like a functional programming language, right? In a functional programming language, I never actually update a value. I just sort of make new variables. And so you can imagine that if we imagine a processor with just sort of like an infinitely many registers, then what I could do is I could say, well, every time I write to a new register, I'm creating sort of a new value. It's kind of the same way that in my functional programming code, when I perform a new operation, I return a whole new value as the result of that operation. And if I'm able to do that, if I had this processor with just sort of infinitely many registers, then I could assign a register for every sort of meaning in my program for every time I use it. So in this example, this write after read example here, maybe I have some operations that use R1 that have significance to this add instruction, but instead of needing to sort of load into R1 when I want to sort of move to a different section of my code, and give this register a new meaning, well, I can just change R1 to R100. If there's an infinitely many registers in my program, then then I can just store val into this register, and now I don't have a problem if these instructions are reordered, because I'm not loading a value which is then subsequently used. These are loading to totally different registers. And then similarly over here, if every time I have a new occurrence of a destination register, if I just give it a unique value, then conceptually I can eliminate these two hazards. Now, of course, a real processor doesn't have infinitely many registers. So what happens is basically in this register renaming step, every destination register gets a unique value, and then also in this sort of step, or maybe down the line, there's a mapping of these sort of pretend registers to the actual registers in the processor, and there's a way that the processor can sort of work out how those instructions are executed in order to use the limited register set a processor has to effectively kind of mimic these scenarios where I'm using I pretend like I have as many registers as I want. So register renaming applies a little bit of abstraction to the code by pretending like we have these infinitely many registers, and then working out down the road how they actually map to the real registers in the processor in a way that eliminates write after read and write after write hazards. All right, but as long as I get this thing working with the cost of a bunch of added complexity, I can increase the performance or the efficiency of my pipeline, and basically many of the most powerful processors, really I would say all of the most powerful processors, like the ones in your laptop, basically use some form of out of order execution in order to achieve their levels of performance. All right, folks, that's all I got. I'll see you next time.